Okay, so we're going to talk about the reactions of benzene. And in the last video, we said if you get benzene, which can be thought of as like that, and you react it with bromine, no reaction. Whereas if you get ethene and react that with bromine, decolorized, and it's an electrophilic substitution electrophilic addition reaction. Now, benzene doesn't undergo electrophilic addition reactions because when you get an addition reaction, let's see with ethene, what happens is you end up breaking the double bond, you add across the double bond. Right, benzene isn't as reactive as alkenes because, do you remember what we said about the electron density? The electron density here between the carbons and the ethene is pretty high. The electron density in benzene is not as high because the pi electrons are not just concentrated here, but because you get electron delocalization, they're spread out over the whole molecule. So benzene doesn't tend to undergo electrophilic addition reactions. Instead, it comes on a new kind of reaction which we haven't looked at yet, and it tends to undergo electrophilic substitution. Well, why is it electrophiles are going to react with benzene? Why electrophiles? Well, if you think of the benzene ring, what have we got? We've got an area of high electron density above the ring and below the ring. Okay, so electrophiles are going to be attracted towards that. So things with a partial positive charge or full positive charge. And you get substitution because addition would mean that the electron delocalization would be broken and it's not as unstable as the situation in just pi bonded alkenes, and so it doesn't undergo addition. Right, we need to think about the mechanism for electrophilic substitution with benzene, and the electrophile I'm going to talk about is something which you won't have come across before. It's the NO2 plus ion. Now, if you're thinking about the bonding, what that's like, you can draw a dot cross diagram for that if you like, but you can see that the nitrogen is forming 4 bonds, and very often when nitrogen forms 4 bonds, like in NH4, it has a positive charge on it. And oxygen always forms 2 bonds. So anyway, you can draw a dot cross diagram for that. You can see that this nitrogen is positively charged. It will only have 4 of its own electrons in its outer shell. You can draw that, but we're concentrating on the mechanism here. So you can draw that as NO2. That's probably a good idea. Well, the positive charge is spread throughout the whole. That positive charge doesn't sit there, actually. It's spread throughout the whole of the molecule. And again, that is electron delocalization, but we won't talk about that. Okay, so here's benzene. Now, when you're drawing these mechanisms, I draw your benzene nice and big because the exam board are very picky about where the arrows come from and you don't want any confusion. So here's benzene. This is our electrophilic substitution mechanism. It's quite a short one. Usually it's only like 3 marks rather than some of the other ones are like 5 marks. So here's NO2, any electrophile, that's NO2. Right, now, what have we got? This circle represents delocalized electrons. There are how many electrons in there? There's 6 electrons. In other words, there are 3 pairs of electrons. So the first step in the mechanism, a pair of electrons from the delocalized system goes and forms a bond to the nitrogen. So we draw that. Now, if it does that, it's going to break the delocalized system, partially break it anyway. So what we're going to have here is we have NO2 is now bonded to that carbon. I've drawn this one here. And just remind ourselves, there's a hydrogen on every carbon, but just remind ourselves, and usually people do draw the hydrogen on that carbon. And now the delocalized system is broken, not completely. And they like you to show it broken from that carbon there to that carbon there. So you sort of draw a horseshoe shape. So be careful when you draw that. Now, when we talked about mechanisms, this thing was neutral, this thing was positively charged, so this intermediate has got to have a positive charge on it. Now, you might think the positive charge would be just on one atom, but the positive charge is actually shared over the whole delocalized system. So that makes it more stable. That makes this stabilizes that intermediate, because the positive charge isn't just on one atom, it's over several. Okay. Now the next step is for we had 6 electron pairs here originally. We've only got 4 in there. 6 electrons, 3 pairs. We've only got 4 electrons, 2 pairs in the delocalized system there. So we've got to put 2 back in. Where do those 2 electrons come from? Well, they come from this bond here. Okay, so that we draw that as that goes back into there. And so we reform the delocalized system is now reformed because we've got 6 electrons, 3 pairs back in there. We draw the NO2 is on there, and the hydrogen, of course, has come off without it's any electrons, so it's H+, and that is the electrophilic substitution mechanism. Now, where does the NO2 come from? Where does it come from? You obviously can't have a bottle of just positive charges. They always got, and it's made in situ. And the way it's made, it's making a generating, and they usually ask this as well, generating the NO2 electrophile. Well, what happens is you need concentrated nitric acid and concentrated sulfuric acid, and together these are called something called nitrating mixture. Right, now what happens is sulfuric acid actually gives a proton to nitric acid, to concentrated nitric acid, and it forms, so if it gives away a proton, that's going to be HSO4, that's minus, that's what's left over, and the nitric acid is going to be H2NO3 plus. It's interesting, what's happened there is that the sulfuric acid has given away a proton, so this acts as an acid. And concentrated nitric acid we think as being a very strong acid is quite weird, because this is actually acting as a base. In that reaction. Then the second part of it is the H2NO3 loses a water molecule. So what is left over is NO2 plus. So I would write both of those equations down. In the exam, it usually says like it says something like, give an equation or equations to show the generation of the electrophile. It's usually phrased like that because they don't tell you what they're not giving away what the electrophile is there, and you'll get 2 marks for that. You can write it as a single. You can combine those two into one equation, but I prefer to write it as 2 equations there like that. So that is another mechanism you need to know. So, and the generating the nucleophile, the electrophile is quite important there, and that is the actual electrophilic substitution. So we'll leave that there.